what to use in your lab. So we have the dilution equation, which is pretty simple. It's M1V1 equals V2. So you'll have a concentration of whatever your stock solution is, and then you know that you want to make a certain amount of a certain concentration, and you can figure out how much of that stock solution you need to put into the water. So, for example, we're just going to dive straight into these problems. Or actually, do these have to be in a particular unit?
They just have to be the same on both sides.
They have to be the same on both sides, yeah. So it's kind of like our gas laws, other than temperature, or if you're using the ideal gas law, they can be in whatever unit as long as they're consistent on both sides. So you can have mass percent actually on both sides. You can have milliliters on both sides, as long as they're consistent on both sides. If they're not, then you have to do some conversion. Okay, so our first problem here, we have a chemist starts with 50 mils of a 0.4 molar sodium chloride solution and dilutes it to 1,000 mils. We want to know what the concentration is of sodium chloride in the new solution. So it's just kind of like the gas laws again. We start off by making a list. We know our M1. What is M1 in this equation?
0.40.
0.40 molar, right? That's our initial concentration. Do we know our V1?
0.05 liters.
You don't have to convert it.
50 milliliters.
Yeah. You can if you want. It's just extra work.
Okay, I see.
Yeah, so we have 50 milliliters. Do I know my M2?
No.
No, this is what I'm trying to solve for. Do I know V2?
1,000.
So for this one, I see I'm trying to solve for V2, so I just need to rearrange that equation to solve for V2. To solve for V2, what is this going to rearrange to?
Wait, M2.
Oh, I'm sorry, M2. Talking faster than I'm thinking. Okay, so we're trying to solve for M2. Well, how do I rearrange this?
Divide both sides by V2.
Divide both sides by V2, so it's going to be M1 V1 over V2. So you plug these numbers in. And you should get like what, 0.2?
0.0.
0.02 molar? And there should be 2 seconds. So you have 0.020 molar sodium chloride solution there. Any questions on that?
It changes it if I don't have an extra. I got 0.02. That changes it.
0.02. Is that the right answer? Is it 0.2? Yeah.
And my order was told.
As long as you get the same answer, that's what's important. Yeah, because that's just like if you plug those in differently and figured it out differently, all that matters is you got the same answer. Okay, any questions on that? All right, let's look at the next question. We have a chemist wants to make 500 mils of a 0.05 molar hydrochloric acid solution by diluting 6 molar hydrochloric acid. And we want to know how much of that solution should be used. So this is kind of what they would do in lab. So do I know my M1?
6.0.
Do I know my V1?
No.
No.
Don't know that. Do I know M2?
0.05.
And do I know V2?
500.
500 mils. Okay. And 0.0. Okay, so for this one, I'm trying to solve for V1. So I just need to rearrange that equation to solve for V1. So if I'm solving for V1, what's it going to rearrange to?
M2 V2 over. Yeah.
So I plug these in and I get that. What is my answer?
0.12.
Yeah,
I got
0.0042, but
Let me just do it.
0.0042.
You might have converted it to liters. You might be reporting it in liters, and others are reporting them in milliliters.
Well, yeah, I did convert.
Okay, so I got 4.2. And then the units for this, what would my units for this be?
Milliliters.
Milliliters. My volume here is in milliliters, so this is going to be in milliliters. So what this means is I would need to take 4.2 mils of my stock solution, put it into what we call a volumetric flask, and they're little flasks that they look kind of like this, and they have this curved line here, and so this will go into I'm making 500 mils. This would be a 500 ml ball flask. I would take that 4.2 milliliters and put it in here, and then I would add water up to this line, and that tells me that I then have this, 0.05 molar solution of hydrochloric acid.
So is the volume always the amount of water and the mole?
The final volume is the total amount of water in your solution.
Okay.
So it's the whole solution. So you would add to this, if you were to figure that out, that would be 95.8. Yeah. That is how much you would add to it. So it's going to be the difference there. So the total solution is 500 milliliters. Questions on that? Okay. Next question is how much of a 0.20 molar glucose solution can be made from 50 mL of a 0.5 molar glucose solution? Same type of arrangement here. Okay, so in this one, what is my M1?
0.50.
What's my V1?
50.
What's my M2?
0.20.
And do I know V2?
No.
That's what I'm solving for, right? Yep. So for this one, we're going to do our M1, V1 over M2. So we have okay, so there's our problem. What do we end up with?
125 milliliters.
Is that what everyone got? We agree on that? Okay. Questions on that one? These seem pretty straightforward. Probably some of the easiest calculations you've done so far.
You should put 10 of these on the
10 of those on the test?
Yeah.
I think I put one of them on the test. I wrote it yesterday, so. Okay, the next topic we're going to look at is solution stoichiometry. When we are doing solution stoichiometry, it's just like any other stoichiometry. We're always going to go through one particular thing. What do you think we're always going to go through? Moles. So it's just like anything else. You always go through moles. So when we look at some of these problems, we want to know for this first one, we want to know how much mass of calcium carbonate is required to react with 25 mL of 0.75 molar hydrochloric acid. And we're trying to solve for that in grams. So for this one, where do you think you're going to start?
0.75 liters. Well, I converted from 750.
Okay, yeah, for this one you'll have to go to liters. You will have to go to liters. Yeah, because molarity, what are the units for molarity?
Moles per liter.
Moles per liter, right? So we do have to go to liters in order to get to moles. How am I going to get to moles of hydrochloric acid?
Moles of hydrochloric acid, the mole ratio from the...
My ratio, right? We're going to use molarity as a conversion factor. So I'm going to say that I have 25 mils. So I'm going to convert that into my liters. So I have 0.025 liters, and I'm going to say, okay, so for that I know that I have 0.75 moles of HCl per liter of HCl. Everyone see where I got that ratio from? So I'm using that as a conversion factor. Any questions where I got that? The Thursday lab, we haven't covered this. We did on Tuesday. Okay. So I use my molarity as a conversion factor. Now what do? Now it's just like any other problem you've ever done.
You go to grams of, well, what you need, which is grams of...
I can't go to grams yet. Where do I have to go?
Moles.
Moles, right? I need to go to moles of calcium carbonate first. So I say, how many moles of hydrochloric acid do I have? So I have 2 moles of HCl to how many moles of calcium carbonate?
1.
Once I get to moles of calcium carbonate, now I can go to grams of calcium carbonate. So I know that 1 mole of calcium carbonate, what's our molar mass here? Did anyone get this? Okay, we'll figure out our molar mass real fast. So calcium's at 40.
I don't know why I skipped that problem. I didn't see it.
You're not the only one, it sounds like. Okay, so the molar mass is around 100. So if you go through and solve this, you find out that you need 9.4 grams of calcium carbonate to react with that much hydrochloric acid. Questions on that one? Yes. Okay, so this is my molarity right here. That's my concentration. This can be rewritten 0.75 moles per 1 liter. That's what it means. So you can just rewrite it that way. So that's why I plugged it in down here. It's the same thing. So this and molarity are exactly the same. Other questions on that? I'm sure you weren't the only one who had that question. You're the only one for That's scary. Okay. Other questions on that? Sorry, when you're sitting moving half a mile in half an hour, you get ornery. So, we got this? Okay. The next question. How many grams of sodium can be reacted with 750 mL of a 6 molar solution of sulfuric acid? And we're given a reaction here. So we're told that we have 750 mL of a 6 molar solution of sulfuric acid, and we're trying to figure out how much sodium we need to react. So where am I going to start on this one?
Convert to liters.
First, I need to convert to liters, and my given is I'm going to start with my given, the volume. So I'm going to start with 0.750 liters.
And then
What's my next step?
your molarity ratio, 6.0 moles per 1 liter of.
So I use my molarity as a ratio, my conversion factor. Okay, now Mariah, you be quiet. Now where? What do I do next? Moles to moles, right? So I go moles of H2SO4 to moles of sodium. So I go 1 mole of H2SO4 to 2 moles of sodium, right? Now what do I do? My molar mass of sodium, which is 23. And then I solve for it. 2.7 or 207. Okay. Which is around 200. Okay. How many of you guys, were any of you guys able to do either of these?
No.
No. How many of y'all have questions on these still?
Block went over it in SI, that's why we.
Oh, okay.
Yeah.
It was just,
Okay. Are we good on this?
no, not.
What is bothering us? I need the feedback. I can't just say, okay, I magically understand what's wrong. Why did I run this one? There's 2 sig figs right here. Yeah. What else? What else has us confused?
So, oh, never mind.
Do we all see where this conversion factor comes from now?
Doesn't it come from the molarity, right?
Always in 1 liter, yeah.
Yeah, they give it.
That comes from the
This
molarity,
comes
right?
from the molarity, yeah. This is the same thing as the molarity. Other questions on this one?
Fill them with their.
Okay, let's go on to the next one. I think there's one more problem here.
No. It's hard to find it out. It's weird, huh? It's so weird.
The book doesn't have any examples of this? Really?
Sometimes when I get emails from the book, I just wait for you to explain it here because it's much more clear than text.
Yeah, that's weird. Huh.
Oh, yeah, me
Well, I probably figured you could use a dictionary. So,
Well, yeah, but you could.
different books have different things wrong with them. So, okay, the next one, I'm asking you how much calcium hydroxide is required to react with 350 mL of applicable molar hydrochloric acid. I did not give you the equation on this one. So this one, you should have first step written your balanced equation. So what is the product between calcium hydroxide and hydrochloric acid?
Calcium chloride.
Calcium chloride and what?
2H2O.
and water. So we have our salt and our water, and okay, so there's our balanced equation. Now we know that we're trying to react our calcium hydroxide with 350 mils of our 0.40 molar HCl. So where am I going to start? My 350 mils, right? Converted to liters, that's my given. So I start off with my 0.350 liters, and then what's my next step?
Molarity.
Yep, good. So I use my molarity to convert to get to moles. I feel like people are getting a little bit more confident.
Yeah, now we understand it. Once you explain it.
We're getting it.
The textbook makes me want to cry.
Don't cry. Okay, so now that I have moles of HCl, where do I go? Moles of my calcium hydroxide, right? So I have my 2 moles of HCl to 1 mole of calcium hydroxide. And then once I have that, I can figure out
Your mole in there.
So I think I got 74 grams. So if we go through and calculate this, we can react that with 5.2 grams of calcium hydroxide. Questions on that? Okay, in the sake of time, we are done with chapter 13. We're not doing freezing point and boiling point. Those are kind of an extra thing that I throw in when we have time, but we do not have time.
Is it going to be on the test?
They will not be on the test. So that is it for chapter 13. The rest of chapter 13. Everything before that. So if it's before that, it'll be on the test. The last Thursday of the month. Oh, test? Oh, the Tuesday. Sorry, yes. So 1.5 weeks. Thank you. Sorry.
So not just Tuesday, next Tuesday.
Yeah, next Tuesday.
The week of Thanksgiving.
Like a week and a half.
Okay.
Is that what that is? It's called fortnight?
I've never, I'm glad I've
That's
never
Shakespeare. I was never good at Shakespeare. Okay, so moving on to chapter 14. How do we do on chapter 14?
Wait, what?
How do we do on this?
Actually,
I only went through
Actually,
pages,
I
right?
feel pretty good.
You guys doing okay on those calculations?
I got a little confused.
Okay, we're going to spend most of the time on the calculations today. Just once again, for sake of time, I'm going to kind of gloss over the theory, and we're going to go towards the calculations. Okay, so today we're talking, chapter 14 is on acids and bases. We hit titration in lab on next week, so this is just focusing on up to that point. Acids, what are some of the properties quickly of an acid? Sour taste,
Dissolved metals, and
dissolved metals,
Separate.
produce hydrogen ions,
You would
and
divide
Litmus
that
paper.
equation.
Yeah,
here.
litmus paper turns red.
Oh, red.
Red. Red with that. Yeah, red with that. Okay, so acids, things like your fruits that you eat, lots of acids in them. Okay, bases. What are the properties of bases? Slippery, bitter, like soap. You ever had to put soap in your mouth? Base.
Mhm.
Never had that pleasure except for accidentally. So. Most of us have gotten it accidentally. Okay, so soaps, those are Drano, that kind of stuff, those are examples of bases. Now, we're going to look at a couple definitions really quick of acids and bases. We have first the Arrhenius definition of acids and bases. In the Arrhenius definition, what is the ion that is produced when I put an acid into water?
H+.
H+. So Arrhenius, we have H+ ion, and then what about for bases?
OH minus.
Okay, big flaw with the Arrhenius definition is this right here. Not always. And also, of course, this right here too, this doesn't exist by itself in water. So instead we like to use the Bronsted-Lowry definition. That was the modified, the newest one that's come out. According to the Bronsted-Lowry definition, what is an acid?
Proton, the H plus ion, it's a donor.
So we have a proton donor for an acid, and what about for a base?
It's an acceptor.
This is the valid definition of acids and bases that we're going to look at. So the Bronsted-Lowry is where we focus most of our attention. With the Bronsted-Lowry, we can actually identify what are called conjugate acids and conjugate bases. What is the difference between a conjugate acid and its between an acid and its conjugate base?
There's one has like electronic.
Yeah.
There's one hydrogen ion difference, yes. So the difference between an acid and its conjugate base is a hydrogen ion. The difference between a base and its conjugate acid is just a hydrogen ion. So if we look at, still have chapter 13 for some reason.
So when you call something like an acid and its conjugate base, it just means that there was a donation and acceptance between those two?
There was, yeah, a transfer of a hydrogen ion. Oh, my arrows are all missing on that. Sorry about this. Okay, so if you look at this, this is an example of an acid-base reaction. We have our pure gas, we put the water, we end up with our bisulfite ion and our hydronium ion. If I ask you to label the acid and its conjugate base, the first thing you have to do is recognize what the acid is. An acid, remember, is a proton donor. So whatever you start with over here, it's going to end up with one less hydrogen over here. So in this case, if I look at H2SO4, it's what gives up my hydrogen. Because over here, it has just HSO4. So this is my acid. It has given a proton. My base is what accepts the proton. So here, H2O has accepted a proton to become H3O+. This is my base. To identify the conjugate acid and the conjugate base, what I do is I just look for the thing that differs by one proton. So if I look over here, H2SO4, what do you think my conjugate base of H2SO4 is going to be?
HSO4.
HSO4 minus, right? So this is my conjugate base. These two are paired. My conjugate acid is my H3O+, and these two are paired. So this is my acid conjugate base, and this is my base with its conjugate acid. This is what we call our conjugate acid-base pairs. So if we look at the next one, and this reaction, what is my acid?
Your hydrochloric.
My HCl, right? So this is my acid. What is my base? Hydroxide is my base. Okay, so if this is my acid, what is the conjugate base going to be?
H2O.
Conjugate base.
Oh,
Cl.
Yeah.
Cl minus, right? These two are paired together. What is my conjugate acid going to be?
Water.
The water. So this one is my conjugate acid. Now, the reason that we can call these conjugate acids and bases is, let's think of if we flip this reaction. Let's flip this top one. Looking at the reverse reaction. If I reverse this reaction, which one of these over here is acting as my acid? Which one's my proton donor?
Your
H3O. H3O plus, right? That's acting as my acid. Notice that we called it a conjugate acid over here. Most chemical reactions don't go just in one direction. They go both ways. There's a few that do. The really strong acids, they only go in one direction. But you'll have a reverse. This one is a strong acid, so this doesn't realistically happen, but just pretend. You'll have this reverse reaction. In the reverse reaction, this is acting as my acid, this is acting as my base. So these conjugate acids and bases actually do have a reaction going on. It's just that the reaction leans very heavily towards that direction for the most part. In this case, that would just go the one way. Okay, looking at the next set here. Okay, so for this one, what is my acid?
hydrochloric.
My hydrochloric acid, what's my base? My ammonia, and then what is my conjugate base? Cl minus, what is my conjugate acid?
Ammonia.
Ammonia minus. Questions on how we're doing this? It's just to differ by one hydrogen. That's all you're looking for. And then the last one here. Okay, for this one, what's my acid?
Would it be ammonia?
Oh, yeah.
My hydrogen donor. Which one gets rid of hydrogen?
Your water.
My water, right? My water actually gets rid of the hydrogen here. H2O becomes OH minus. It's one less hydrogen. So what's my base?
Ammonia.
Sorry, I thought you
And then what's my conjugate acid?
said ammonium.
Ammonium. And my conjugate base is then hydroxide. Okay, questions on that? Okay, neutralization reactions are just basically whenever you add an acid and a base together. What are the products of a neutralization reaction?
Water and
Water and salt.
Water and a salt. It's a form of a double replacement reaction. We've already talked about these. You've already done calculations with them. You just didn't realize that at the time necessarily that you were doing acid-base reaction. And you've actually already done titration calculations as well. You just don't know it. Okay. Acid reaction. How do acids react with metals?
Some can dissolve a metal.
What do they form as one of their products usually?
A gas.
A gas. Okay. So let's look at the samples down here. If we look at hydrobromic acid, what is hydrobromic acid? HBr. And it reacts with nickel metal. What is it going to form?
H2
and nickel.
NiBr.
Nickel is a 2+, yeah. Okay, so whenever acids react with metals, they form hydrogen gas as a product. So that hydrogen goes away, and they end up forming the salt as a product as well. If I look at hydrofluoric acid, so what is hydrofluoric acid? HF plus calcium oxide. Okay, I can do hydrogen gas and calcium fluoride, but what happens to the oxygen?
Oh.
Water?
Wait a
minute.
You can have water, can water be a gas?
Oh. Yeah.
Yeah. And then balance the sucker.
Wouldn't the
The top
first
one would be balanced. If you
Oh yeah, I didn't balance top one, sorry.
Yeah.
Put it 2 there. I left that unbalanced. Okay, going on to bases down there. What is the only other base reaction that can occur other than neutralization? Sorry, what? Sodium hydroxide. Sodium hydroxide with aluminum. I'm trying to remember what I pulled out from the text on this one.
I got the same thing.
Sodium hydroxide and aluminum and water.
Reaction of sodium hydroxide with aluminum and water. That's what it said.
We're gonna skip that. I didn't
Oh
say
yeah,
that.
so
Not
the only
important.
other kind of base reaction that we covered.
Okay, we're gonna keep going. I can't remember exactly what I was looking for there. I'm
It's
focused on
490.
getting EPA called me right now. Yeah, I need to get there fast. Okay, strong acids and weak acids. What is the difference between a strong acid and a concentrated acid?
A strong acid will completely
Completely
ionize.
ionizes.
So strong acids, we're talking about the ionization. So a strong acid, I mentioned over here that some of the reactions are reversible. Strong acids are not. So, for example, the hydrochloric acid, when it is put into water, it goes completely into our hydronium ion plus a chlorine ion. 100%. It does not go backwards. There's only 6 strong acids. Every other acid, the reactions are reversible. This is very different than concentration. Concentration is how much solute is in a solvent. It's not talking about dissociation. So there's a big difference between the two. A strong electrolyte, this is basically something that dissociates completely in solution, and it will conduct electricity very well. So very good conductors of electricity. All right. So the 6 strong acids you guys can look at. Same thing with bases. There's not very many strong bases. There's 6 strong bases as well. You do need to know those. All right, so let's go on to the water part. We're going to be going over now concentrations and calculations. So that's what I want to spend the next 12 minutes on. So when we look at water, water is what we call amphoteric. When I say amphoteric, what do I mean? What can something that's amphoteric do?
Be an acid or a base.
Be an acid or a base. So it's very unique because it can act as an acid or a base. When you have water, like those of you who are sitting there with bottles of water on your desk, that water is not just sitting there as water. What is actually going on is there is a continual chemical reaction in that water. You have neighboring water ions reacting with each other to form hydronium and hydroxide ions. Now, there's a very small percentage of hydronium and hydroxide in your water at any given time, but it is there. There is a relationship that has been found to be constant, and that is the concentration of hydronium times the concentration of hydroxide ions is always equal to 1 times 10 to the negative 14th molar. That never changes. So if you know the concentration of one of those, you can figure out the concentration of the other. Problems with this, yes, you do. Okay, so if I'm looking at trying to figure out the concentration, let's just do something easier. If I say that I have a concentration of OH minus that equals 1 times 10 to the negative 4th, what is my concentration of hydronium going to be? How do I figure that out? If I know that's my equation up there, how do I solve for this? Yeah, what I'm going to do is I'm just going to divide this 1 times 10 to the negative 14th by my concentration of my hydroxide ion. So if I know hydroxide, I can figure out hydronium just by doing this. I can also just do the vice versa. If I know my hydronium ion concentration, let's say my hydronium ion concentration is 1 times 10 to the negative 11th, how do I figure out my hydroxide ion concentration?
By the hydrogen.
This divided by that, right? So my hydronium ion, or my hydroxide ion concentration is just that 1 times 10 to the negative 14th divided by my hydronium ion concentration.
So pretty much the first one is like the hydronium ion is a given, and then you're just dividing it by the formula.
In either case, you always take 1 times 10 to the negative 14th and divide it by whatever the other one is. And I don't know why this throws people so much. My only guess is because we start throwing in really negative exponents. Because you guys all give me blank looks, and it's like it's just a negative exponent. I'm pretty sure that's what does it. So it's just the 1 times 10 to the negative 14th divided by the whichever one you know. That's all you have to do. Questions on that? Okay. So you can figure out hydronium or hydroxide ion of anything as long as you know either one of those. Now, when you're doing this, if you're having calculator problems, please come up and ask me or raise your hand when we're going through practice problems so that I can help you figure out your calculators, because I won't help you on the test. Because I won't be here on the test. Don't worry, yours will still have the test. I know that you'll be sad if it got canceled though. Okay, now the next important thing to look at here is the pH. So we're going to go from these hydronium and hydroxide ion concentrations to pH. What is pH?
It's a scale for the acidity or basic acidity.
Yeah.
It's a scale for the acidity or basicity of something. Basically, it gets rid of all those negative exponents, and it puts something in terms that we can visualize a lot more easily. It's a logarithmic-based scale. So that's the pH scale. Now, how do we determine the number of sig figs when we're doing pH calculations?
Was it decimal?
The original number of sig figs gives you
It tells you the decimal places, right? So if I have, in this case, I have one significant figure, I would have decimal places. So the number of sig figs in the original, equals the number of decimal places. So that tells me that the number of decimal places in my pH will tell me the number of significant figures in my concentrations as well. It works both ways. All right, so pH. is equal to the negative log of your hydronium ion concentration. You can also figure out pOH. The P is just a function, that's all it is, and that's equal to the negative log of your hydroxide ion concentration. So that P is a mathematical function, that's it. So when you have your calculators, there's certain tricks, and I kind of gave you a link on some tips for that if you don't know how to use your calculator, but like I said, you can ask me as well. So in order to figure out the pH, all you're doing is just taking the negative log of the number. That's it. So for this first one, we're told that we have a hydronium ion concentration of 4.35 times 10 to the negative 6. So to figure out our pH is just the negative log of that number. How many of you guys were able to do this? How many of you guys tried to do this? Okay, so get out your calculators. Don't just stare there at me, because if you do, I'm going to be annoyed when you start asking me, how do I do this? So many calculators, you do log of the number, or some other calculators, you might type the number in first and then do the log. It depends on your calculator.
So it should go either way, right?
It should what?
If you put log before or after, one of them should work, but both of them are saying error.
How so?
It depends on what calculator you have.
And then it goes log.
I have a feeling you have to enter yours. 6, right? Yeah, you enter yours and then push log.
Oh. And then because hers comes out in negative, she just changes
And
to a
you just
positive.
negate it. Everyone's is going to come out in negative unless you enter in the sign. I always just do it in my head, because it's not that hard to make a negative and positive in your head. So you should be getting something like, let's see, there's 3 sig figs.
Professor, you did not put any signs in, right?
I didn't put any signs in. Well, I did on the exponent, but I didn't negate it. I just did the negative in my head. pH is always going to be a positive number. pOH will always be positive.
Wait,
The
what?
pH and pOHs were always going to be positive numbers. So you don't really have to, like, because when you take the log of 4.35 times 10 to the negative 6, you get negative 5.36. I just flip that in my head. I don't type it into my calculator. Yeah, so pH is always positive. Okay, did everybody get this on their calculators? Any questions on how to do this? So, like I said, some of you have to enter the number in first and then push log. Others of you will type log and then hit the number. The concentration of hydroxide or hydronium? Yes, that's a given. That's what's in the problem now. Yeah. Okay, are we all good? Okay.
Yeah.
So you type in your 4.35. Oh my God, you type on 4.35.
Undo the log.
Other questions? And by the way, cell phones don't count as calculators, right? So make sure you practice this on a real calculator before you actually show up for the exam. Okay, so that's the first one. The second one we have, we're told that we have a hydronium ion concentration of 8.21 times 10 to the negative 12. So for that one, our pH
I don't know.
how many sig fig or decimal places, sorry, should that one have?
3.
3. So remember, we're going to decimal places. So this one's going to be 11.086. Questions on that? We're not looking at significant figures. We're looking at decimal places. So you figure out the number of sig figs this one has, and that becomes your decimal places. So I had 3 sig figs. I have 3 decimal places. 3 sig figs, 3 decimal places. Yes. No, it's just the number. There are no units for pH. Other questions on that one? Okay, now, the next question I asked is how do you calculate the hydronium ion concentration from pH? So we're going to go backwards. So this is going from hydronium concentration to pH. You can also go backwards. So to figure out your hydronium ion concentration, it's 10 to the negative pH. So it's another mathematical function. So you take power 10, raise it to your negative pH. That's your hydronium ion concentration. Hardest part, learning how to do it on your calculator. So for this first one, we're told that we have a pH is 12.87. So that means that our hydronium ion concentration is 10 to the negative 12.87. So a lot of times you'll have, some of you might have like an inverse log function. So there's like a 10 to the x. You would type in your number first and then do the 10 to the x. Or you might type in the 10 to the x and the number. It depends once again on your calculator. So go ahead and try and figure out that to make sure it works. Now for this one, when you figure out your answer, remember the number of decimal places tells you how many significant figures you have. So how many decimal places do I have here? 2. So I'm going to have 2 significant figures in my answer. So that's why I rounded this to 1.3. So go ahead and try that. Make sure you come up with the same answer in your calculators.
Yeah.
What?
You still need help, Maya? You got it.
Aisha, do you have a question?
Okay.
And you pretty much always make it negative, right?
Which one?
Like, if they give you the pH,
Yeah.
you're always
Other
going
calculator questions?
That's what it says in the book. It shows you. It says that if the number is positive, you make it negative to get your positive answer out of it. The book actually had steps how to do it as well.
Yeah, I thought it did, but it doesn't always get read in practice. Okay, so you type in your number first, so it's 12.87, you negate it, and then the second log, that's where the 10 to the x is, and that tells you your.
Oh, okay.
Other calculator questions? Just do 12.87, type in 12.87, negate it, and the second. Okay, everyone else good?
Why wouldn't the 6
Any other questions?
for the last 5 minutes?
Okay, so that gives you your concentration of your hydronium ion. The next one, your concentration of hydronium is simply 10 to the negative 3.8. So if you do that,
So you would not have 4 decimal places? Like the rule of 6 figs for this one doesn't apply?
it's the however many decimal places you have is
Okay.
how many sig figs you have there.
So it's,
So if you have 2 decimal
okay.
places, you have 2 sig figs.
All right.
So yes, opposite. So for this one, in this case, how many sig figs should I have in my pH? One. I have one decimal place, one sig fig. So this would be 2 times 10 to the negative 4. When you round that. Okay, questions on that?
Is that negative on the calculator?
Yeah, you should have that negative 4 showing on the right-hand side. There should be somewhere over there.
Would it be wrong if you put 1.6 times 10 to the negative 4?
It should have one significant figure, so you will lose points for sig figs. Okay, on the next page, we're going to stop here and get off the quiz, but we're going to finish this. We have time built into the schedule, so we'll finish this on Tuesday. But I want you to see this next page, this chart right here. These charts, I love giving these on exams, and I can tell you I gave you one on the exam because I wrote the exam yesterday. So what I want you all to do is to work on this for next week. You know how to do this. So your job is to finish this for next week. So Tuesday, I want you guys to come into class having tried to finish this. Okay? That's your assignment, if you will, on top of your assignments. It should theoretically be done. So, okay. Go ahead and are there any questions before I give you guys a quiz?